Hey guys, what's here? Welcome back to Project Moisture, and today we are going to be looking at some of the hardware of this bad boy, the circuits that I've created. They're probably going to have like maybe 2 videos on this topic. So let's take a look at the actual circuitry here. We got it up here. If I can get my stupid Photoshop working properly, you can kind of break it down into 3 parts here. You've got right here, we have this is the Raspberry Pi. This is the whole brains of the operation, the thing that runs our Python program, runs that on top of Linux, and gets all the stuff done. Here, this big one here on the breadboard, this is like 90% of this is just the safety circuitry, the fail-safes. So yeah, it's the lion's share of the circuitry for sure. But today what we're going to talk about is this bad boy on the bottom right. This is a perf board. I soldered it up myself with lots of wires and lead, and it does mainly, this is all just power stuff. So everything related to power is on this board. All right, now what you're seeing here is a schematic I scanned from my notebook that I kind of used to design this whole thing. And you can kind of break it down into 2 parts. And top here is the power stuff that we're going to be talking about today. And the bottom is stuff for the safety circuitry. So in the top, let's break it down. We're going to break the top down into 3 parts. This is power, basically voltage step down. This is actually, says 9 volts. It's actually 19 volts here. This thing steps that 19 volts down to 7 volts. This part here, this is all to do with the actual, the valve. This controls the on-off of the valve. And this one here takes the 7 volts from here. This gives you 7 volts here. And this turns that into 5 volts that's needed by the Raspberry Pi and by one part of the circuit down here, this part right here. So we've got basically 2 voltage regulators, 2 supply circuits, and then the control of the valve. So let's talk choices. Why 7 volts? Well, the valve here is rated at 12 volts DC, but I found that I could run it could actuate reliably down to 7 volts. So that's the voltage that I choose. Obviously lower voltage, we're gonna have less current, less power. So I said, yeah, let's make this thing more efficient. We'll run the solenoid for the valve at 7 volts. Now my power supply is 19 volts. And you might say, well, why don't you choose a power supply that just does 7 volts? And I didn't have one, right? I needed a power supply that was beefy enough to push the amps required by the solenoid, which is like, I don't know, maybe like 1.5 or something. I forget what it was when I measured it. But it's not like it's not a small amount. It's not a tiny amount of amps. So I needed a decent power supply. And the decent power supply that I had was 19 volts from an old laptop. So I got 19 volts. I got to take it down to 7 volts. Now you'll notice, okay, so these 2 circuits here, these 2 chips, they're both things that take a larger voltage and regulate it down to a smaller voltage. This one is taking 7 down to 5. This one is taking 19 down to 7. And you look at these 2 circuits here and you see that this one here is significantly simpler than this one here. So why didn't I use the 7805 or similar part for this job over here? And that is an interesting topic that the main thing that I want to cover in this video. So let's say we attach some kind of load to the output of this regulator here. And that load is such that it's going to accept 1 amp at 5 volts. Okay. And let's say that the input to here, we'll pick an easy number, we'll say 10 volts. So this regulator is regulating 10 volts down to 5 volts. Now, the way these regulators work is that if the load is drawing 1 amp, the input is also going to draw more or less 1 amp. And it's just going to drop the volts How does it do that? Well, I mean, a little bit of, thermodynamics, call it 1 amp times 5 volts. So you're supplying 5 watts to the load, but you're drawing in 10 times 1, 10 watts, which means that 5 watts has to go somewhere. And where it goes is you get 5 watts of heat out. So what happens is you just get a very toasty part very fast. You're going to have to put a heat sink on that. And as you can see, if you turn this to 20 volts, say we put the supply in at 20 volts, then you're going to have to dump 15 watts of heat and you're going to get 5 watts of actual work. So you're wasting 3 times the energy that you're actually using. That's the problem with these, I think they're called like a linear regulator. They're very simple, but they're not efficient because whatever voltage they drop, they basically just have to dump that out as heat. Now this guy here is called a buck converter, and they operate on a different principle which allows them to be quite a bit more efficient. So you'll see here, we've got a little component. This is called an inductor. It's basically just a big wound wrap of wire. Let's see if I can show you what an inductor looks like. So that inductor in the diagram, that's this guy right here. It's a big wrap of wire, usually around some kind of a core, like a donut-shaped iron thingamajigger. Iron donut. To understand what this guy does, I think the best visualization is if you can think of like a flywheel, like a mechanical, just a big heavy wheel, and it's got a very smooth bearing. It rotates very well, but it takes a lot of force to get it moving. Once it's moving, it's hard to get it stopping. You can spin it up, and that stores energy in the rotational motion of the flywheel. And take a look at this. The Price is Right. This is the wheel. This, you could say this is like an inductor, like a big flywheel. She did a pretty hard job to get it moving. But once it's moving, it spins for quite a while and it slows down slowly. So that's what this inductor is. It's hard to get moving, but it's also hard to stop it from moving once it is rotating. Except in this case, it's not rotation, it's the current flow through this thing. So when you apply a voltage, you're not initially going to get much current flow, but the current flow will go up and up and up as this thing builds energy. And it builds energy in a magnetic field that gets stronger and stronger. So that is how an inductor works, pretty much. So what you're going to see here is this LM2596 has 19 volts in, and it is going to apply pretty much that full 19 volts to here. And that is going to start this inductor charging up, start it spinning. So it's going to start off at 0, milliamps, but slowly and surely that is going to grow and grow, and you're going to get more and more current flowing through here. So initially when you have 0 milliamps, this thing is basically acting like an open circuit. So you'll see 19 volts here, you'll see 0 volts here. But as the current, as this thing kind of spins up, you're going to see more and more volts here. It's going to climb to 1 volt, 2 volts. It's going to climb to 7 volts. And if you keep letting it go, it'll climb to 8 volts, 10 volts, 15 volts. But we don't, remember, this node here is our output. We want to keep it at about 7 volts. So what do we do? Well, the way it works basically is, you can see here, we've got this connection going back into here, and here's a feedback into our regulator here. So this is how the regulator senses what voltage is currently being output. And when that voltage gets to around 7 volts, it's going to shut off the flow here. So now we have no connection to the 19 volts here. But remember, this is like a flywheel. So it's going to keep trying to, it's going to try to keep this current flow at this level, which will keep this voltage at around 7. And then, as this current flow supplies current to whatever needs the current, you will lose energy and the voltage will drop. And when the voltage drops, this thing is going to sense that, and it's going to open the flow of 19 volts here, which will then spin this thing up again. And then it'll spin down and spin up and spin down. So you'll get like a kind of like an oscillation, right? And if you turn the supply on and off very fast, at a very fast rate, your ripple here is going to be very low, and you're basically just going to get a straight DC 7 volts. That's the idea. Just a quick addition here. I did mention that this line here is basically the feedback, and that's how this module senses what the output voltage is, and that's how it can know when to turn itself on and off, right? Connect this to this. But what I didn't mention was that the values of these resistors here is actually what determines the output voltage here. So by changing these values, you can, have it output 9 volts or 12 volts or 4 volts, whatever. These control the desired output voltage. Now, there's some problems that need to be overcome. So in this case, cutting off that flow here doesn't mean that it goes to 0 volts. What it actually means is that this connection here is completely severed. All right. Now, the funny thing about your inductor is once you got it spinning, and let's say, it's got, let's say, 1 amp of current going through it, for simplicity's sake. If you just try to disconnect the circuit here, it is going to, at that instant, it can't just instantly drop from 1 amp to 0 or anything like that, right? It is going to make sure that there is no discontinuity in the current flow, which means if you, for example, had a switch and you open the switch contacts, it would still try to pull 1 amp across that air gap, which means that now instead of, maybe having 19 volts develop across that gap, you're going to get, maybe several thousand volts. So imagine, you've got the Price is Right wheel here and you got it spinning, and then you said, okay, I want to stop it. And you just kind of jam your pinky finger into the spokes. What do you think's going to happen? You think it's going to instantly stop that wheel from spinning? Or do you think your pinky finger is just going to snap the fuck off? Because I'm going to tell you what's going to happen. You're going to lose that finger. And it's the same idea for inductors. You can't just cut the current and expect good things to happen. And in our case, we don't want that, because we want this inductor to keep supplying energy when we cut off the 19 volt supply. So that is what this diode is here for. When you've got 19 volts here and it's supplying energy, the current's not going to flow in this direction at 19 volts. So this is like a one-way valve, a one-way street for current. But when you cut this connection off here, this inductor is still going to try to spin 1 amp through the circuit. It can't get it from here, but it can suck the electrons from, this is connected to, you can see here it's connected to ground, so it can suck those electrons from 0 volts up to, the required potential, which at this end would be 7 volts. So that is basically how this thing works. It's going to supply 19 volts until this thing spins up and we get our desired voltage here. Then it cuts off the supply of 19 volts. This thing keeps spinning, and now it's going to suck electrons from ground and supply them from here. So you've got electrons coming from the supply, and then you've got electrons that have been sucked from ground up into here. And so what that means, let's say a load requires 1 amp. This supplier does not have to supply 1 amp because some of those electrons are going to be coming from ground. So this thing supplies less than 1 amp. Now, how much less depends on all the efficiencies, which depends on, how you select your inductor and, this circuit itself. But, and I don't know the typical efficiencies of these things, but I don't know. I think they're probably like around like 80% or something. Just my gut feeling. I haven't tested this and I won't test it, but I would imagine that this thing is probably like, on average, supplying 500 milliamps. And this part here is supplying 1 amp because this is like less than, the output voltage is less than half of this. So maybe like 500 milliamps versus 1 amp. Whereas if we had it in, if we use this kind of circuit to do the same job, we'd have to suck 1 amp at 19 volts to supply 1 amp at 7 volts, and we'd have a huge amount of energy being dumped out as heat. But the ability of our electrical flywheel to suck electrons from ground up until the potential that we need, that's what allows us to be more efficient. I just want to make a little disclaimer here. I never looked up what a buck converter, like how it works. This is what I infer from the circuit. So I could be wrong. And if I am, be free to correct me in the comments. I'd love to hear about it. I'm basically giving you my conjecture as to how these things work based on what I know about the components that I see. But I mean, I wired it up and it does work. So I know it works. And I'm pretty sure that this is how it works. But if I'm wrong, let me know. Now, the other things here, these capacitors, it's pretty common to have capacitors at, the inputs and the outputs of your regulators. They kind of just smooth the output, right? If there is a sudden increase in the amount of current that needs to be drawn or a sudden decrease, right? These things will kind of act like buffers to adjust to that more easily. I mean, I could give you just one extreme example. So let's say we've got again, we have a load and it is drawing 1 amp. So that means that we would have, 1 amp flowing through this inductor. Now, all of a sudden, the load, there's a switch in it, there's a transistor, and that transistor becomes closed. So now, let me think here. If there's 1 amp, so that means that before you would have seen a resistance of about 7 ohms on that load, and that drops to 0 ohms. No, wait, wrong. That drops to infinity ohms, or 100 mega ohms or something. I don't know, whatever. A very big number. Well, what do we know about inductors? Inductor doesn't care about your changes in resistance. It says no, I am going to push 1 amp no matter what resistance you put in there. I'm going to push 1 amp until I run out of energy in my electric field, more or less. So that means that, let's say, okay, let's just put real numbers in here. Let's say it becomes 1 mega ohm resistance. So that's 1,000,000 times 1 amp. That means you're going to develop 1,000,000 volts across that component, which means that your transistor that you had there to close the gate, basically, that transistor is now dust. You have released the magic smoke. It's not a good thing. But if you have, let's say, a nice big capacitor in here, when your load says, okay, I'm now a giant resistor, what happens is, okay, that current just basically gets dumped into your capacitor here. Your capacitor charges up a bit, and yeah, you're going to get a little bit over voltage, but you're not going to go to 1,000,000 volts, right? You're going to go to a number significantly lower than 1,000,000, but somewhat more than 7. So that's one of the reasons why you would have this capacitor here. It's a little place for the current to go when it doesn't need to go into the load. So when you have changes, when your load fluctuates in how much current it's drawing, this capacitor will be able to pick up the slack in both directions, right? If it suddenly says it wants more current, well, this inductor isn't able to do that immediately, but this capacitor can supply electrons to meet that demand until the inductor spins up to that amount or whatever. So, these capacitors, they're buffers basically. They smooth things out very nice. And can also have a protective effect. And that's it. I mean, that's just, the basic idea is that if you need 1 amp, you don't have to draw 1 amp from here. You can draw significantly less than 1 amp to get 1 amp out. How much less depends on the difference between these two voltages. Whereas here, the bigger the difference, you're just going to get very hot very fast. And you're going to waste a lot of electricity in the process. So there we go. That's how that works. And the rest of the circuit, I mean, that's basically what I wanted to talk to. I just wanted to discuss the idea I have in my head about how this works, because I think it's very cool. I think it's very cool, and I think it's very legal. And buck converters are great. So we now pretty much understand what this does. This part of the circuit, not too complicated. The solenoid, which is this here, the thing that opens and closes the valve, that's actually just basically like another inductor. It uses a magnetic field to pull something that, opens the valve. All right. So we want to control that. So we put a power transistor here. When this input goes high, meaning, more than like 1.5 volts or something, that will allow current to flow through here with basically zero resistance. And that means that the current will flow like this, and the valve will open and water will flow out of the tank. Now, here's the fun thing. Let's say we've got solenoid is open, we're draining, and we say, okay, we want to close the valve. So we bring this low. This component now becomes like, let's say, a 1 mega ohm resistor. But we previously had 1 amp flowing through here. And as I've mentioned, this thing is just basically a coil. It's basically an inductor. And what do we know about inductors? They don't care about your changes in resistance. They're going to push 1 amp, which means that you again are going to release the magic smoke out of here and say bye-bye to your transistor. And maybe even the resistance will go so low that it'll open your valve and it'll flood your house too. Just a bonus right there. So that's what this is here for. Because this is actually, if you look at the numbers, that's the exact same diode that I'm using over here. So it might seem weird to put a diode in the wrong direction. Current is supposed to flow in this direction, but we're putting a diode in this direction. What the fuck? Well, when this transistor turns off, basically we didn't disconnect this part of the circuit, the current can't flow through here, but if we have this diode right here, the current could flow back up through here. And so it basically the current loops through here until the magnetic field, burns itself out. And that is why this diode is actually called a freewheel diode. So it allows the inductor to freewheel until its energy runs out, instead of just busting your transistor wide open. So that's why that is there. Fun fact. So it's a similar idea to the transistor we have here, but, slightly different, right? This one is essential just because we need to suck electrons to keep the power going and to get our efficiency of the inductor. Here, we need it so that we don't blow up our transistor. But again, if we didn't have this one here, we just blow this guy up. So, it's kind of different, but also the same, but also different. Insert meme.gif. Yes, I said GIF. Don't at me. All right. So that's this part here. And then the last part here is, I've already talked about that. That's just the linear regulator that takes us from 7 volts down to 5 volts. And because this is only going to supply the pi, which requires much less current than the solenoid, and because it's only taking 7 volts down to 5 instead of taking 19 down to 7, it's a much safer design choice to use this one for doing that conversion regulation. It doesn't waste nearly as much energy. And, as you can see, the circuit is a lot. I don't even have this part in here. So it's only this one capacitor here. So this was a much simpler circuit to put in than all this stuff here. and the waste of energy is pretty much just insignificant. We don't have to worry about it. And there you go. There's the entire thing. I mean, here you just see I've got a switch that basically just connects the entire thing to the power supply. So I can turn it on and off without unplugging it from the wall. And then here I also have an LED that just tells me whether or not it's on or off. That is my power indicator. And I thought 4.7 kilo ohms would be enough, but it's not. This thing is way too bright. So, but I'm not going to change it because it's all soldered in there. And it's not a huge amount of electricity wasted anyways. It's just very bright at night. I had to put something to cover it here. So just to put everything in its place, this is the 5 something something. This is the buck converter IC. Again, like I said, this is the inductor. This is the diode for the buck converter. This is the input capacitor. And this is the output capacitor. You can see that they're different sizes, even though they're both 1,000 microfarads, because this one is rated at a higher voltage, obviously, because the input is 19 volts. The output is only 7. So that's why this one is bigger than that one. Other things. Okay, so this here is the 7805. The linear power regulator. Here's the output capacitor for that, which is even smaller because, we're regulating a much smaller current there. So I figure we can get away with a smaller filter capacitor. I just wanted some filter on there because this is going into digital circuitry. So you want to keep it nice and clean. This is the switch for the solenoid. And this is the diode for that solenoid switch. So that's pretty much all the main components here. A few resistors, you see one poking out here. You can see a resistor here. You can see a resistor here. You can't see it, but the power switch is actually right here. So the power switch and the LED are on a board, on a very tiny board, also perf board, that is actually on the outside of this box here, but I didn't get it in this picture. Yeah, one more thing I wanted to mention, this regulator here, whatever you want to call it, these things are generally known as switching mode power supplies. And the name comes, like I said, when you get up to 7 volts, it turns off. And then when it drops a little down, it turns on again. And it does that very fast, very quickly, so that the ripple is small. So yeah, it's switching. So here's what I imagine it looks like, basically, if you were to check out the signal from here. I've never actually checked it, but yeah, it should look like this. And then the signal from here should basically be like, if this is, 19 volts here, then you'd have your 7 volts down here, and it'd basically just be a straight line. But I think if you zoomed in a little bit, you'd see like little wiggles, right? Because it's gotta go up and down at least a little bit. You know what? Well, you know what would be fun, actually? What if I just hooked up an oscilloscope and we just looked at what it actually is, and then we can kind of use that to compare and see, at least to a certain extent, how much my prediction of how it works is actually accurate. That might be fun. One second. Let me see if I can. This is going to be hard to record, but let's give it a shot. If not, if it doesn't work out, I can just remove this part of the video and you'll never be the wiser. All right, check this out. So I've got my oscilloscope set up here. I've got the probe connected across that diode. So let me just show you on the diagram here. Yeah. So we've got the probe across this diode, which is actually going to, because one end of the diode is connected to ground, and the other one is connected to the output of the regulator. So this diode will basically tell us what voltage is being applied to the, the inductor. And as we can see, as I assumed, it's basically, yeah, it's a square wave, right? Turning on, turning off, switch mode, as they call it. And it's interesting here. We can see it's kind of jumping around. I got it re-triggering on the oscilloscope. But if we look at the left-hand side of the square wave, I don't know what you call it. The rising edge, I guess is what you call it. The rising edges, they all are fixed on the screen, basically. They're all at the same place. And what that means is that I think the the frequency is fixed for this regulator. So it runs at a fixed frequency. The interesting part is that the frequency is fixed, but if you look at them jittering around, it looks like the duty cycle is not fixed. And that makes sense because, if you got something like a CPU, it's not always consuming exactly the same amount of electricity. It varies from, millisecond to millisecond, microsecond to microsecond, depending on what it happens to be doing at that instance in time. Now, one more little interesting experiment that I would like to do here. I've got SSH into the Raspberry Pi right now, and I want to change what it's doing. Right now, it's probably mostly idling, and we get this duty cycle. I want to see what the duty cycle change looks like, if any at all, when I stress the CPU to its maximum. I want to see if that actually changed, if we can actually know, because there already is a bunch of jitter. We might not even be able to notice with our eyes how much change there is, but we might be able to. So I want to try and see if I can notice a change in this when I run the stress program, the stress utility. All right, so I got it on stress CPU 1. Let's see what happens when I press enter. I'm gonna go onto the screen here, and I'm gonna press enter. Okay, interesting. What's happened is basically before we were seeing the duty cycles kind of switch between high duty cycle and low duty cycle. But now when I turn the stress on, it's now just locked at this duty cycle. So I guess this is basically the maximum. And what we were seeing was a fluctuation between the maximum and the idle as the CPU was, sleeping and turning on at a very high rate. So if I do a Control C, let's see, let me show you here. Yeah, dispatching 1 hogs. Now I'm going to do a Control C here, and it should go back to doing the jumping and jiving. Yeah, we're going back there. We got our jump and jive back. So, and I think, yeah, this one is back on just idling at the command prompt here. And we're back to jumping and jiving. So that's interesting. We can actually see the effect of the CPU's usage on the duty cycle coming out of our regulator. Very neat. All right, check this out. I put another probe on here. So I connected the negative, or the ground thing of the probe to the same spot, but I put the other part of the probe on this diode here. So now I got 2 probes. Yeah. So let's see. Take a look. Too many probes on this bad boy. I got too much shit on me. You can see it's a crowded party here on one side of that diode. But here, so I got this hooked up, but I don't have the circuit turned on. By the way, this is the thing that didn't show up in that picture, where we got the power switch. And as I mentioned, it's too damn bright. I don't know if you can tell how bright this is, but it's too damn bright. But anyways, so again, we've got this bad boy giving us our circuit. Now let me turn on channel 2. Is it going to give us anything? I don't see anything. I don't know what that's. Channel 2 is set to 200 millivolts. That's too many millivolts. Wait, that's too few millivolts. We need it set to there we go, 2 volts per division. So you can see, yeah, we've got 7 volts coming out of there. And it's more or less, just a flat line. It's got a little noise on it, as you will. But mostly it's just a nicely regulated 7 volts. Not too bad. But what if we were to zoom in on that now? All right, check this out. So I zoomed in on the y-axis of our second one now. So it's 200 millivolts per division. And I scrolled it down so that it came into view. And here's what we see. So now we can actually see the ripple that whose frequency corresponds to the frequency of our switching mode thing here. So we've got our square wave here, and that is what is giving us this kind of ripple going on in our output. So, I mean, I don't know, it's 200 millivolts per division. So, I don't know, maybe like 50 millivolt ripple or something like that. Somewhere around there. Anyways, there's probably things I could do to calculate that, but I don't actually give a crap. I was just mildly interested. What if we were to play around with the time step here? Get the time step bigger. Yeah, we can see some. It's mostly just that ripple, but at the discontinuities of the input square wave, we can see little jumps and jives. You know what I'm saying? You're picking up when I'm putting down here. So what if I were to like just stop one of these bad boys? Stop. Yeah, we can kind of see it there. It's still pretty hard to tell. What if I were to juice it up? Yeah, we can start to see there's like a little ringing. That is what you get, these oscillation in here. Let me just zoom in so I can tell you this thing here. You get those, especially when you've got like inductors and capacitors together. They have a harmonic frequency, and you can kind of see the ringing in there. That's cool. Let's see if we can pick up the other one. So if I scroll the horizontal position over a little bit, come over, center it on this bad boy here. Now let's juice her up. Oh yeah, we get a nice big fat ringing in here. Stop that. There we go. Look at that. Yeah, so you get these things in here which are, not great. That's a pretty big spike here on that output. But that'll be further regulated. So like that is, where's my finger? That's the voltage here, which is the voltage here, which is the voltage that comes into here. But that gets further. I didn't add this capacitor, but this capacitor would probably help out with that a little bit. And then this output capacitor here and this circuit itself helps out a little more. So you get even less, distortion, whatever you want to call it, noise coming out. But yeah, it's just interesting to look at this stuff. It's fun to look.